Hello and welcome back to Timberwolf Tutoring. I'm Robin, and today we'll be going over the topic optimization. So here's an overview of what we'll be doing in this video. To start with, we're going to conceptualize what optimization is and why it's important, and then what you're going to need to know to use it. Then we're going to go over 3 problems. The first one's going to be simple, the second one's going to be a little bit harder, and the third one's going to be more difficult but also more of a real-world application than the other two. Even though optimization is basically exclusively for real-world applications, which is really nice. So, conceptual a bit. Optimization is applying the stuff that we know about calculus to the real world. So you might see problems like this. Maximize the area enclosed by a given amount of fencing. Choose the price that maximizes sales profit. Or find the closest point on a circle to another point. And if you're looking carefully, you might notice what all 3 of these problems have in common. And this is, they all want you to find a value that maximizes or minimizes some quantity. And we know that maximum and minimum are both our relative extrema. So what we're trying to do here is solve for a relative extrema given a function. So for instance, the first one, this fence problem, let's do an example right now. But first, here's how you solve an optimization problem. So step 1 is going to be rewrite the word problem using algebraic expressions. So like for instance, in your fence problem, if you're given the amount of fencing, you might write that 2 times length plus 2 times width is equal to perimeter, which we know. Number 2, find the quantity that you need to optimize. This is going to be the thing that they ask you to maximize or to minimize. Number 3, rewrite that quantity in terms of a single variable. So usually it'll be a double variable expression, like area equals length times width. What you're going to want to do is use your other expressions to isolate all but one of those variables, and then plug them back in so that you only have to have one variable in your expression. Number 4, take the derivative of this new function and find all the relative extrema. And then, once you have this, you usually only have one, occasionally you have more than one. And these are all going to be minima or maxima. And to figure out if it's actually the one you want for the problem, you're going to use the second derivative test, or the common sense test, if the problem is easy enough, to figure out which of these extremes actually is the minimum or maximum you're looking for. And finally, you're going to find the actual answer to the problem, because frequently it won't be asking you for like length, the variable that you didn't isolate. It'll be asking you for area, so you're going to have to go plug that back into your formulas to find the area. So number 1, here's an example fence problem. So say you have this one. Find the maximum area that can be enclosed in a rectangular region using 40 feet of fencing. You can write 2 equations just from this information, using L and W for the length and width. So we have 2L plus 2W equals 40, because that's the perimeter of the fence. And A, or area, is equal to L times W. So isolating L is the first step. So we divide both sides of the first equation by 2, and subtract W from both sides, and we get L equals 20 minus W. And we plug this into the area equation, and we get area equals 20 minus W, all times W. Or 20W minus W squared. Then we take the derivative. A prime is equal to 20 minus 2W. So A prime is equal to 0 when W equals 10. And L would also be equal to 10 in this case, because 2L plus 2W equals 40, and L equals 20 minus W. So now we do our check step by using the second derivative test. The second derivative of 10 is negative 2, because A double prime is just negative 2. There's no W in there, so you can ignore the 10. And it is less than 0, meaning this is a relative maximum. Remember that less than 0 means the maximum, and greater than 0 means the minimum for second derivative test. And finally, we solve for what the problem asks for, the maximal area, which is length times width, which is 10 times 10, or 100. So now our next problem, we have the same fence problem, but reversed. So, minimize the amount of fencing needed to enclose a rectangular area, divided equally into 2 pieces by a fence parallel to one of the sides, if the area is 600 square units. So don't let the wording intimidate you. It's just a square divided, it's just a big rectangle divided in half. And it's not divided in half diagonally, it's divided in half the usual way. So, because of this, we have to count one of the variables in the perimeter equation twice. So it would be 2L plus 3W, or 3L plus 2W, it doesn't matter which one. Because you have to count that extra line down the middle. as part of the perimeter, because we're counting the amount of fencing, not only the outside perimeter. And then again, we have L times W equals 600, because the area is 600. So now we're trying to minimize F. So again, we isolate one of the variables, which in this case we can isolate L, but it doesn't matter which one. So L is 600 over W, or 600 times W to the minus 1. So then we plug this into our area, or sorry, this is supposed to say fencing equation. But yeah, fencing is equal to 2 times 600 over W plus 3W. And then we take F prime. I'm sorry, that's supposed to say F above, not A. But yeah. We have F prime is equal to 3 minus 1200 W to the negative 2. So F prime equals 0 when W equals 20. And plugging this in, we get L equals 30. We double check, take a second derivative, and F double prime of 20 is 0.3, which you can verify for yourself that it's true. And if greater than 0 means is a relative minimum for the amount of fencing. And finally, we calculate the perimeter, and we plug in 2L plus 3W, and it's going to be equal to 120. So now here's an interesting one. It's a formula for weather. And the problem is a bit wordy, but basically it's saying that this function, d of x, models the amount of daylight in Vista. And this is very, very close to the actual function in real life that models daylight. Because you'll notice that on the solstice, it'll be dimmest or brightest, and on the equinox, it'll be exactly at 12. But 12 at the beginning of the equation is the average amount of daylight, and then the amplitude of 2 on the cosine is meaning that the amount of daylight will increase or decrease by 2, which is about accurate. And then you'll notice the scalar 2 pi over 365 inside cosine, which means that it will have a period of 365. So anyway, we want to maximize the amount of daylight, which means we need to maximize this function d of x. So there's no rearrangement necessary, we just have to take the derivative and find the extrema. So we take d prime of x equal to 2 sine of 2 pi over 365, you get the idea. We just use chain rule by taking derivative of cosine, which becomes negative sine, and that cancels out with a negative sign already there. And then we multiply by the derivative of the inside, which is 2 pi over 365. And the 12 disappears because the derivative of a constant is 0. And so now we set this equal to 0, and to do that we just need to set sine equal to 0, because everything else is just a constant. Just a constant multiple. So we set that sine of 0 is equal to 0, and sine of pi is equal to 0, and also 2 pi, 3 pi, etc. So we just want this to evaluate something dealing with pi. So we know for a fact that negative 13 will work, because that plugs out 0. And then we can also increase x by 365 over 2 as many times as we want, because when we multiply that by 2 pi over 365, that'll just get pi. So we can write that like this. And now we're only going to consider the two cases falling within the current year, because any other case can just be considered the same date but in a different year. So the two cases we have are 352 and 339 divided by 2. So now, since we have two cases, we're going to have to figure out which one's actually the correct answer by using our second derivative test. So it's more important here than in the other ones where it's just check step. So here we have d double prime of x is 2 cosine of 2 pi over 365 times x plus 13 times 2 pi over 365 squared, because we've had to multiply by that constant both times we've used chain rule. And now, plugging in x to both of these, if you want you can pause the video and try it yourself. But the answers are that 339 over 2 is the only negative one. So this date is the maximum, because negative second derivative means it's a maximum. And we can count 170, not 173 days past January 1st. And we find this date is June 20th. And this is the actual summer solstice this year, if you want to look it up. And that's why formulas like this are so cool, is because just by using your calculus knowledge and applying it properly, you can calculate the summer solstice. Anyway, that's optimization for you. Thank you so much for watching our video. We hope you enjoyed it, and that it helped you learn optimization a bit better. If you need to contact us to ask us questions or request another topic of your choice, you can email us at timberwolftutoring@gmail.com or tag us on Instagram at Timberwolf Tutoring. Let us know if you have any questions or comments on this video. We appreciate the feedback. Again, thank you so much for watching this video. This is Robin and the rest of the Timberwolf Tutoring team, signing off until next time. Have a great day.